In this tutorial, I explore the subject of camera rotation order and create a simple rig to facilitate more intuitive camera manipulation. When animating cameras for visual effects, one must often work within the constraints of how a real-world camera platform is capable of moving. The ability to translate a camera in any direction is greatly facilitated with the use of cranes, helicopters, skycams, and drones, but many of these platforms are still limited in their ability to rotate a camera in any fashion. They mostly utilize a form of rotational mount that follows a particular rotation order. Here is a typical example of such a mount for a crane or motion control platform. The three rotation axes are configured with the pan or sideways rotation on the top and outside of the order. Attached to the pan axis is the tilt or up and down rotation. Then last, the roll axis is attached to the tilt axis and rotates the camera around the optical axis of the lens. In Blender, this rotation order is specified as YXZ. The first axis, reading left to right, is the bottom of the hierarchy. Y is parented to X, which is parented to Z. Since Blender's world is defined as Z up, pan rotates around the vertical Z axis. Tilt rotates around the X axis, which is horizontal left and right, and the Y roll axis passes through the lens front to back. I have constructed a simple model to emulate this arrangement. As I rotate the top Z-axis, the X tilt and Y roll axes and camera follow along. Rotating the X tilt axis reorients the Y roll axis and the camera, whereas rotating the Y roll axis only rolls the camera. You can basically think of this as an exploded view of the three-axis manipulators offset from their common center of rotation. This makes it easier to visualize how the separate rotations interact. This configuration also closely mimics the way we view the world from the platform of our own bodies. Here I have the same camera rig linked to a model human to demonstrate the similarities. I downloaded the model from makehuman.org, for which I will post the URL in the description of this video. The camera rig is flipped over, so that the pan axis is even with the hips of the model, and the camera is even with the eyes. Our neck, which is connected to our hips, behaves like the X tilt axis that rotates our head up and down. Our neck also rolls our view around the axis between our eyes, similar to the Y roll axis of the camera. If you look down and rotate your hips, it is the same motion path a camera follows on a crane head. If you look straight up and rotate your hips, your view rolls about the axis running down your body, and you experience gimbal lock between the pan axis of your hips and the roll axis of your neck. Since this is a common and natural method of rotating a camera, it makes interpreting a camera motion graph easier and more intuitive. Each distinct rotation is represented exclusively in its respective motion graph. To achieve this same rotational behavior using any other rotation order results in several axes contributing to a single emulated axis rotation. Let's see how this rotation order works with an unmodified Blender camera. I'll create a new camera and set all of its transforms to 0. Then set the rotation order to YXZ. Let's also set the manipulator orientation to gimbal to properly simulate camera rig behavior. That looks odd. The camera's initialized 0 rotation is pointing straight down. I'll just rotate it 90 degrees on the X tilt axis to level it out with the world. But now I just lost my roll axis. Right from the start, we are already in gimbal lock.
Gotcha!
Blender's default camera orientation pointing straight down defies the natural initial viewpoint looking forward and parallel to the ground. Tilting the camera 90 degrees to achieve a level viewing angle immediately places the pan and roll axes in gimbal lock, in which the Y roll axis aligns with the Z pan axis, and the ability to roll is lost. The Blender camera in its unmodified form is useless for emulating this common real-world rotation order. At this point, to achieve the desired result, one must construct some form of camera rig. Camera rigs are very common in 3D animation and take an endless variety of forms from simple to complex, depending on how much control one wishes to have over the camera animation. Studios that produce pre-visualizations for movies often construct complex rigs that accurately model the particular camera platform that will be used to film the movie. There are a couple of camera rigs included in the default installation of Blender as an add-on. To load these rigs, go to the File menu and open the User Preferences, then click on the Add-ons tab. Under Categories, choose Camera and check on Camera, Add Camera Rigs. Then save the user settings. To create a rig, go to the main 3D View menu bar and choose Add Camera. Then choose Dolly Camera Rig or Crane Camera Rig. This creates a fairly elaborate set of transformation controls, which I won't explain in this tutorial. My goal in this tutorial is to demonstrate the simplest method to achieve a proper emulation of real-world camera rotation. First, let's create geometry to serve as the camera's control object. From the Add menu, select Empty Arrows. Make sure the empty's location and rotation are set to 0 and set the rotation order to YXZ. Also, let's name the empty something more meaningful, like Camera Mover. Just double-click the object name in the outliner and rename it. Next, create a camera, either from the Tools Create panel on the left or from the Add menu, Camera, Camera. Set Location Rotations to 0, then set Rotation X to plus 90 degrees. Set the rotation order to YXZ. Also, I'll name the camera Camera Persp to identify it as the actual camera object. Now go to the Main Properties panel and click the Constraints tab with the chain link icon and create a copy rotation constraint. For the target, choose the empty we created, then check on Offset. Next, create a copy location constraint, and again choose the empty as the target. Lock all the camera translation and rotation axes so that we can't accidentally move it out of position. Now let's look through our rig camera by pressing Ctrl-0 on the number keypad. In the center of the view, we see some intersecting angular lines. If I select them, I see that they are the Y-axis of the camera mover empty. We somehow need to make that not visible through the camera. We can do that by moving the camera near clipping plane farther away from the camera to exclude the empty's geometry. In the Main Properties panel, select the Camera tab and find the Clip Properties Start and End. Set the start to 1.5 and notice the obstructing lines in the camera view have disappeared. To test the rotational movement of the rig, we need to set the Transformation Manipulator controls to Gimbal and set the Pivot Center to Individual Origins. Select the camera mover in the outliner and press the 0 number pad key to change the view back to the user perspective camera. Through that, we can observe the orientation of the rig camera. There are three methods you can use to rotate and translate the camera: the transformation input fields as sliders, the viewport manipulators, or the R and G hotkeys. Each method effectively isolates rotation to a single axis, and each preserves the integrity of the real-world platform emulation. To rotate the camera, first select the camera mover. Using the transformation input fields as sliders, left mouse click down in one of the rotation fields, such as X, and move the mouse sideways, left or right to tilt the camera up or down. Click in the Z field to pan the camera side to side, and in the Y field to roll the camera on its view axis. To rotate the camera using the object manipulators, click on the manipulator icon in the viewport menu bar, or press Ctrl spacebar to toggle the manipulators on and off. Make sure the transformation mode is set to gimbal. Select an individual axis ring to isolate the rotation to a single axis. Viewing the manipulators in gimbal mode also allows you to monitor the status of potential gimbal lock as the Y and Z manipulator rings approach alignment. To use the R and G hotkeys to move the camera, first make sure the transformation mode is set to gimbal. Press the R key, then double-tap one of the axis keys X, Y, or Z to isolate rotation to one axis in gimbal mode. The colored axis line will appear to indicate the axis of rotation. The viewport menu bar will change to the operation status line, indicating you are in rotation gimbal mode for that axis. Move the mouse to rotate, and move the rotation cursor farther away from the center of rotation for finer control. Left-click to accept the rotation change, or press Escape to cancel the operation. Remember, the camera mover arrows will always indicate the camera's local orientation, and the manipulator axis will indicate the camera's gimbal or rig movement orientation. When the rig achieves gimbal lock, the empties Y arrow and the green Y manipulator will align with the manipulator's blue Z arrow, or the blue and green manipulator rotation rings will align. This will happen when the camera is aiming in the absolute vertical direction up or down, with X rotation at plus 90 or minus 90 degrees. When camera animation keyframing is complete, you can bake the final animation into the camera and remove the constraints so that the camera moves on its own. This may be necessary when exporting the camera animation to another application. To bake the keyframe animation, select the camera, not the mover empty. Unlock the camera's translation rotation channels. In the toolbar animation menu, click Bake Action. Set the keyframe range to Bake, and check on Visual Keying, Clear Constraints, and Overwrite Current. Then choose Bake Data Object. After baking animation, the camera channels will have their own keyframes, but they will be different than the camera mover if the respective rotation orders were different. Look out for anomalies in the baked rotation channels, such as offsets and gimbal flips. These are common issues when baking animation, but can be easily corrected with some minor surgery on the keyframes. Simply select the displaced keyframes, then type G to move the keys, then Y to move vertically. Then type in the offset amount to move the keyframes. Gimbal flips usually show up as 180-degree offsets. Now the camera can be exported, or the animation curves can be exported, to another target object with matching rotation order. To simplify the construction of this camera rig, I have consolidated the steps into a small Python script, which I will post in the description section of this video. To run the script, open the text editor, then in the menu, either click the plus in the text block browser or select Text menu, Create New Text Block. Copy the script text from the YouTube description and paste it into the text window. Then click the Run Script button at the bottom right of the text editor menu bar, or select Text Run Script from the menu bar. I hope you found this tutorial informative and helpful, and the simple camera rig potentially useful. Please feel free to offer any comments or suggestions that might improve upon its usefulness, or any suggestions on its implementation. Thanks for watching.